Here we continue the discussion of temporal dynamics in social media, studying in particular time series analysis and event detection. So this is just the first of 4 areas in this module, focusing on using timing information in social media to understanding something about the real world. So we've talked about motivating questions for this module. First, how can we detect events using social media data? How do social media networks evolve over time? And how can we model the spread of content in social media? So here we're going to focus on just this first question about detecting events and characterizing them using social media data. Now we've already talked to some degree about time series analysis when we talked about content mining and using the timestamps embedded in social media content, especially tweets, to understand something about the real world. So here, this is an example of time series data from social media postings around unrest in Ferguson, Missouri in 2014 around the murder of Michael Brown, where we see just the beginning of a demonstration at around 7 p.m., peaked in conversation around 10 p.m. We have another peak in conversation at 3 a.m. and 1 p.m. the next day, corresponding to other kinds of events. So the use of tear gas, or the arrest of a Washington Post reporter, or President Obama's speech addressing the nation and trying to deal with these issues. Now, a lot of this is based on parsing of timestamp data from social media content. That's one really good way of generating this kind of time series data. And we've talked about some ways that this time series data gets used for understanding things like the correlation between Twitter and stock markets, and being able to use Twitter signals to better buy or address asset procurement or stock trading in markets, and the questionable efficacy of these kinds of approaches. And we've seen other things that you actually should be able to do much better now in terms of connecting sentiment in tweets over time to attitudes towards public officials or political candidates. So this paper, that I mentioned before, is from 2009, looking at the 2008 presidential election, and it connected Gallup polls about people's approvals of or interest in particular candidates to their discussions of candidates in social media. And now you can do this kind of thing with the tools that we've talked about in the content mining module, where we can extract content and evaluate its sentiment for attitudes for or against particular candidates. We've talked about being able to extract timestamp information from these social media posts, and then you can create this time series data of sentiment scores for individual candidates. But when we talk about trying to do this sort of time series analysis, we constantly have to go back to this question of what time frames are we looking at? Are we interested in tweets per day, as we see here? Are we interested in tweets per minute or tweets per hour? Or is there some additional or more fine-grained or less fine-grained kinds of analysis that we want to do? And the answer here is really that what time frame you want to look at is often extremely context dependent. It depends on the kinds of questions that you're trying to answer. For instance, if we were trying to understand earthquakes using social media, as with the Sakaki et al. Paper, then perhaps tweets per hour is sufficient, where we see in the immediate aftermath of an earthquake, lots of people post over the next couple of hours, and then the conversation dies down, and then an aftershock occurs, and lots of people post again maybe the next day when that aftershock occurs, and so on and so on. So tweets per hour is sufficient. But if we're looking at more temporally fine-grained events or more short-lived events like football matches or World Cup matches or the Olympics or some sporting event, then tweets per hour is certainly or almost certainly not sufficient, because these kinds of events look or occur on a much more compressed scale. And maybe you need to look at tweets per minute or tweets per second to understand more about what's going on or actually see the sub-events around these particular instances. So now we want to turn to this question of how do we detect these kinds of things? How do we look for these moments in time or these interesting moments in these events? And here for the football matches, maybe this is relatively straightforward. We just look for frequencies that are above some threshold, because these thresholds look to be about the same in sort of size and duration, and maybe that will work fine. But if we're looking at more sophisticated and more interesting kinds of events, like the earthquake case, where we have events of different duration and different intensity, we also have bursts or these spikes in conversation that can potentially be nested. So we have to do some potentially more sophisticated kind of analysis here to address these sort of differences in the kinds of spikes or bursts in conversation for things like different duration, different intensity, different structure. And if you want some sort of real-world motivation for the value in this kind of analysis, or understanding what's going on very quickly using social media, you don't have to look very far. So here, for instance, this is from this image is taken from the Boston Marathon bombing that occurred in April of 2013. And if we look at the time series or the timeline of events here, we see that a bomb exploded at the finish line of the Boston Marathon at 2:49 p.m. And moments later, people were talking about this kind of about this event on Twitter, with information even down to the street that this occurred on. As I said, this was conversation that occurred 3 to 5 minutes after the event, where we get what's called situational awareness information, or even geolocation information about what exactly has happened and where that event has happened. And of course, this isn't directed or specific to the United States or specific to that one event. We can see other examples, and more recently at the 2016 Brussels airport bombing in March, where again we see people posting about these events, both the explosion at the airport and the follow-up explosion at the metro station. An hour later, people are posting information and pictures and video of the event and telling us where that event occurred. And in fact, following these events, the authorities in Belgium used social media as a way to communicate to their community. So extracting this kind of information quickly from social media has a lot of value, or understanding what's going on social media has value in this immediate kind of sense. So now we can ask this question: how do we find these moments of high impact? Well, how do we find events in social media? So we already talked about just looking for these kind of spikes, but how do we do that really? Well, the general form of this kind of question is part of a task called burst detection, where you try and identify these bursts in social media. So the general form is you have some signal, some set of events that you can bin up into time slices. So you have some sort of time series, either per minute, per hour, per day, per week, etc. And you try and search for these peaks in discussion. Where are these peaks occurring, or how can we identify as we're in the sort of lead up to one of these peaks? And you could have multiple ones, and you try and identify each one of those, even if they have different intensities. So there's a lot of work on this, but what I'll try and do is give you a sense of how this kind of task is performed, using a relatively naive way of doing this detection. So here, say you have a number of people who are posting about a particular event. Say it's an earthquake, and earthquakes are particularly good examples for this kind of thing because they affect a large number of people very quickly, as opposed to hurricanes, which affect a large number of people but affect them more slowly. So you have different temporal granularities here. But for now, let's say we're talking about an earthquake. An earthquake occurs, lots of people talk about it, there's some lead up to it, and we have some frequency graph that looks like this. Now, how do we identify or flag that there is some sort of burst going on? Now, you could imagine doing some straightforward sort of thresholding approach where, if we have more than 100,000 tweets in a minute, or 100,000 tweets in whatever our time step is, that constitutes a burst. And maybe that's sufficient if you're looking for specific kinds of bursts, but you have to understand or keep in mind that population differences are going to mean bursts of different size are very common. So an alternate approach would try and characterize this line in some way. Now, a typical kind of approach you may use from your geometry algebra course could look at the slope of this line, but clearly this line is not linear, so we need to do something to this data to put us in a position where we can actually analyze it in some relatively easy way. The standard approach for this kind of thing is to take this data, this frequency data, and apply logs to it. So we look at this data not in its raw frequency, but in the logarithm of this frequency. Now, primarily this is because we expect bursts to exist in this sort of exponential space. And if you think about this, this makes sense, right? So an event happens, it affects a number of people, those people tweet about it, and then those people's friends see those tweets and then amplify them to retweets, where they also experience the event in some delay or lag time, or people have to get their phones out and then tweet about the event. So you expect there's going to be some sort of build-up, an exponential build-up in this kind of conversation. So we can look at this content in log scale, and immediately we see a much nicer sort of curve here that we can then apply standard kinds of linear analysis to. The most simple being maybe you just look at the slope of this trend line. What is the change in y over the change in x? What's the change in frequency of the log frequency over your change in time? And then you can use some analysis there. Either you rank these moments by slope, so you build some sliding window that goes over the data you've collected every 30 time steps or so to get this estimate for m. And then you can rank your moments based on the ones that have this highest slope value. Those are going to be the events with, or the moments with the highest burst. Or if you're looking at a more real-time sort of streaming context, then you could apply some sort of thresholding mechanism here as well, where if you're experiencing some burst that increases above some threshold for m, you set off some alert, or you trigger some additional processing to say, an event has happened here, let's respond to it. Now, as I mentioned, this idea of burst detection is its own subfield of research. There's a sort of seminal paper about Burstian hierarchical structures and streams by John Kleinberg from the early 2000s. This focused on email and used hidden Markov models to evaluate what's the most likely set of bursts in his email stream, trying to understand, well, what events were going on that might be associated with these events, or what events are going on that might be associated with these bursts in my email discussion. So once we have these events, or understand that some event is going on, that's all well and good, but now we want to do something more. Let's try and describe what's going on during these events. This is a summarization task. So we have identified some event, and we want to summarize, what is going on during that event. And a relatively straightforward way to do this is take what we've learned, or what we've just discussed about looking for bursts in the tweet stream, and apply it at the individual token level. So here, if we're looking at the case of a football match, then rather than looking for just these bursts in tweets, we can look for bursts in the token stream. So when these kinds of bursts happen, not only are the tweets bursting, but also the tokens within these tweets are experiencing some increase in usage. And we can use that information at the token level to then rank tokens by the ones that are experiencing the most use, or the most increase in usage, or experiencing bursts here. Now, this is a computationally intensive process because you have to maintain potentially sliding windows over whatever your time step interval is for every token in your data stream. And if you were just trying to do something like, well, let's look for goals during the World Cup or something, or let's look for touchdowns in American football, or let's look for a pre-specified kind of event, you can do that in an easier way. But by looking at these tokens and trying to rank them by bursts in a data-driven way, you often get much more interesting kinds of insight into the events. So here you may think, since this is a tweet stream around a football match in the World Cup, that these spikes would coincide with goals. Well, the reality is, as I said, you can get some more interesting kinds of insight. In the 2014 World Cup, a lot of drama existed around the player Luis Suarez, who ended up getting penalized for biting opponent players. And lots of people were talking about this on social media, and this led to bursts in some unexpected kinds of tokens, like the player's name, Suarez, or bit or biting, when people were talking about this particular event. So this gives us a nice way to summarize these kinds of events beyond just some event happened here. And we can see other examples of this. So continuing with the World Cup in football example, in the Brazil versus Netherlands match, early on in the game, the Netherlands player Van Persie scored a goal based on a penalty. And you see tokens that were bursting around this time were goal, Holland, penalty, and the score of the game. Likewise, later on in the game, when Oscar scored, or when Oscar received a yellow card, you see conversation around the yellow card, like for diving, that it was a penalty. And then in the final match between Germany and Argentina, when Götze scored a goal at the end of that match, you see lots of people talking about goal, the player's name, and even discussions of the goal across language. So the token level temporal dynamics in social media gives you information not just about the event, but also about the event across language. So there's real value in the temporal characteristics here. And as I mentioned, burst detection, event detection, this kind of work is its own subfield in social media mining or social media analytics. So if you want to know more about how this technology works, or how you might try and apply it or use it, or what the cutting edge is for doing event detection in Twitter or other social media platforms, it's a good survey paper here from last year that talks about this. Now, a reasonable question here is, great, we can identify events, we can do summarization. What does this really mean? How do we use it? What are some interesting questions you may ask? This is a totally legit question, especially if you're looking for information in social media from, urban populations or highly dense urban areas, where oftentimes social media is most used, so you get most insight from these places. But densely populated urban areas often have many different ways where you can collect information or understand what's going on in the real world. So what's the value here? Reasonable question. Well, platforms are trying to use this kind of technology to understand the world themselves, provide its users, or their users, their own sort of solutions to this. So Reddit has what's called live threads that were used for understanding what's going on right now. Twitter came out with Twitter Lightning, which became the Twitter Moments offering, which looks for topics and then tries to collect conversation or stories around these topics, partially curated, partially algorithmic, but working on the same kind of, we want to identify some sort of topic and event, and then we want to provide information or provide you new information about these events sort of as it happens. There's been some research into this actually about, what kind of event is Twitter in particular, or social media maybe more generally, even good at for this kind of detection. So this paper, Can Twitter Replace Newswire for Breaking News?, asked this question. And what they found was this really interesting result, that journalists are better at breaking political and business news. And this may make sense, or this makes reasonable sense to me, where business news, mergers, or leaks about upcoming earnings or these kinds of things, or political news often require some kind of connection, that some journalist knows somebody to get the story, or journalists, by having credentials, can go to meetings or press conferences and learn something about what's going on. Twitter instead is much better at detecting and summarizing sort of unexpected events, either disasters, terrorist attacks, celebrity news, things that people weren't necessarily looking for, but then lots of people have interest in. And then Twitter is also good for the long tail discussions, once discussions have really dropped off the radar of journalists for whatever reason. So there's differences here in the kinds of events that you can use this technology for. But I also want to talk about a different kind of use of this kind of technology. So here, these are a couple of tweets in the aftermath of Hurricane Sandy talking about how the New York Stock Exchange flooded, or posting this image of the Statue of Liberty being hit by a pretty significant wave. Or these tweets about the Boston Marathon bombing and what ended up being false arrests or false reports of arrests of the Boston Marathon bombing suspects. So both of these sets of tweets, completely untrue misinformation, not necessarily disinformation. They weren't actively being promoted as being false for some malicious reason, but they still got a lot of coverage on social media. Same with this tweet or this story about a Ghanaian football player contracting Ebola, and this example we've talked about a number of times about the Associated Press's explosion at the White House. Now, all of these cases are examples of misinformation, and misinformation that became popular and viral on the platform. So ideally, you'd want to be able to respond to these kinds of events and debunk them as the information spreads, or stop these pieces of misinformation from spreading early on. But in order to find these pieces of information, especially ones that are becoming popular, oftentimes you have to have some sort of algorithmically driven or data-driven approach that helps some analyst or some human person surface these stories and then respond to them. And the event detection and summarization techniques that we've just talked about provide some method of doing that. This is particularly important today, or in today's world, where political misinformation is sort of rampant on the platforms, and the platforms need to respond to this kind of information rapidly. So going back to the motivating questions for this module, the first one, how can we detect events using social media? Now you've gotten some insight into how you might do this, at least from a naive perspective, and some resources about how you might do this in more sophisticated ways. Importantly, though, the time series aspect of the analysis that we just talked about actually is really useful more broadly than just event detection. I'm not going to go into a lot of detail, but I will tell you or go over or provide some survey of the kinds of ways that time series analysis gets used using social media data. So this paper is a good example of the use of time series analysis across social media platforms to understand something about these platforms. So this paper by IS735 and others, part of the iDrama lab, tries to understand what the influence connections are between online platforms. In particular, they want to understand what the influence is or what level of influence fringe communities have on more mainstream communities. And they do this using Hawk's processes on the time series data from Reddit, Twitter, and 4chan. And what they find, surprisingly, was that 4chan and conspiracy-focused subreddits on Reddit exhibit a surprising and maybe unnerving amount of influence on more mainstream spaces like Twitter, which is important if we want to understand how do we improve the information quality of these platforms. More recently, Josephine Luquido published this paper about coordinated multi-platform disinformation campaigns, looking specifically at the Russian Internet Research Agency and their activity on Twitter, Facebook, and Reddit. And what she used was a form of statistical analysis called vector autoregression that lets you evaluate the connection between multiple time series streams, and she used this information to estimate cross-platform effects of this disinformation campaign, specifically looking at whether posts on Reddit, Facebook ads, or tweets were driving behavior on these other platforms. And surprisingly, what she found was that the Russian IRA, their behavior, their campaign on Reddit sort of drove the campaign on these other platforms, which is somewhat surprising. You wouldn't necessarily expect, or at least I would not necessarily expect, Reddit to be the first mover, the first source where these campaigns might go. But at the same time, if we connect this result with the result that we just talked about from Savas's paper about how fringe communities on Reddit exert some surprising amount of influence in more mainstream communities, then perhaps this result makes sense in that context. Looking beyond just antisocial behavior on social media, this paper, Who Leads, Who Follows, by Pablo Rivera at USC and a number of people at NYU, provides a much more sophisticated, multifaceted kind of analysis where they use topic modeling and vector autoregression to evaluate interactions between politicians and the public, specifically trying to understand whether the public is driving the agenda or whether politicians are driving the agenda. And what this means is the public identifying a set of topics that they care about, and then politicians respond to them, or are politicians and political elites identifying a set of quote-unquote important topics, and then the public follows those. Using time series data from Twitter and content analysis, they were able to evaluate and differentiate how Democratic and Republican politicians respond differently to the public, both the general public and the more politically engaged public, and the mainstream media news system. Beyond just research, though, there's commercial aspects for this. There's a company, Storyful, that uses social media to do intelligence gathering and understand the real world. GeoSpark Analytics uses social media as a form of open source intelligence that gets integrated into a number of other signals they use to understand what's going on in the real world. So that'll do it now for our discussion of event detection and time series analysis. So if you have any questions, feel free to post them in the discussion forum.